Look around you right now. Every single thing you can see, touch, or imagine exists within the universe. But here is a question that has haunted humanity for thousands of years and continues to baffle even the most brilliant minds in physics today. Where is the center of it all? Where is the exact point from which everything emerged? The answer is going to challenge everything you think you know about reality itself, because the universe does not play by the rules you expect. If you love the content, leave a like and subscribe to the channel, because this journey to find the center of the universe will take us from ancient civilizations who were absolutely certain they knew the answer, through revolutionary discoveries that shattered those beliefs, and finally to modern physics, where the truth becomes stranger than any fiction ever written. For most of human history, finding the center of the universe seemed like the easiest question to answer. Just look up at the sky and watch what happens. Every single morning without fail, the sun rises in the east and sets in the west. The moon follows its predictable path across the heavens. The stars wheel overhead in perfect circular patterns, completing their journey every single night. To ancient observers, the conclusion was obvious and undeniable. Everything in the cosmos was moving around us, which could only mean one thing: we must be at the center. The Earth, our home, had to be the fixed point around which all of creation revolved. This was not just a casual observation or a simple mistake made by primitive people who did not know any better. The geocentric model of the universe was a sophisticated scientific framework developed by some of the greatest minds in ancient history. Around 380 BCE, the Greek astronomer Eudoxus created the first comprehensive model of a geocentric universe, designing it as a series of cosmic spheres containing the stars, the sun, and the moon, all built around the Earth at its center. This was elegant mathematics combined with careful observation, and it made perfect sense based on what they could see with their own eyes. But Eudoxus was just the beginning. As Greek astronomers continued to study the heavens, they noticed problems with their models. The planets did not move in simple circles as expected. Sometimes they appeared to slow down, stop, and even move backward across the sky in what astronomers call retrograde motion. This should have broken the geocentric model completely, but instead it led to even more sophisticated versions of Earth-centered cosmology. By around 150 CE, Claudius Ptolemy of Alexandria had developed the most advanced geocentric model ever created. He placed Earth at the absolute center of everything, orbited first by the Moon, then Mercury, Venus, the Sun, Mars, Jupiter, and Saturn. These were the only planets known at the time, and to complete his system, he surrounded everything with a sphere of fixed stars. Ptolemy's model was not simple, but it was incredibly accurate for its time. He introduced concepts like epicycles, where planets moved in small circles while simultaneously traveling in larger circles around Earth. This allowed his model to predict planetary positions with remarkable precision, good enough that it would remain the dominant view of the universe for more than 1400 years. Think about that for a moment. For 14 centuries, nearly every educated person on Earth believed with absolute certainty that they lived at the center of all creation. This was not just astronomy, it was philosophy, religion, and common sense all rolled into one unshakable truth. The geocentric model fit perfectly with the worldview of ancient and medieval civilizations. It placed humanity at the very heart of existence, which seemed appropriate for beings capable of reason, art, and contemplation. The heavens moved around us in perfect circles because circles were considered the most perfect shape, and surely the cosmos would be organized according to perfect mathematics. The model was taught in every university, preached from every pulpit, and accepted by virtually everyone who looked up at the night sky. To question whether Earth was the center of the universe was not just scientifically radical, it was philosophically and religiously dangerous. Yet despite its long reign and widespread acceptance, the geocentric model had problems that could not be ignored forever. The calculations required to predict planetary positions became increasingly complex and cumbersome. Astronomers had to add more and more epicycles to their models, creating elaborate mathematical gymnastics just to match what they observed in the sky. The model worked, but it was becoming unwieldy, like a theory being held together with duct tape and wishful thinking. Something was wrong, but it would take a revolution in thinking to figure out what. In 1543, a Polish astronomer named Nicholas Copernicus published a book that would eventually transform humanity's understanding of its place in the cosmos. His revolutionary idea was both simple and terrifying. What if Earth was not at the center of the universe at all? What if the Sun held that position instead, with Earth and the other planets revolving around it? This heliocentric model was not entirely new. In fact, the Greek scholar Aristarchus of Samos had proposed a sun-centered system way back around 270 BCE, but his ideas had been rejected and largely forgotten. Copernicus revived and refined this concept, backing it up with mathematical calculations that made it impossible to ignore. The Copernican model solved many of the problems that had plagued geocentric astronomy. The strange retrograde motion of planets suddenly made perfect sense. When Earth, moving in its own orbit around the Sun, passed slower-moving outer planets like Mars, those planets appeared to move backward against the background stars, just as trees along a highway seem to move backward when you drive past them. There was no need for complicated epicycles or mathematical tricks. The apparent motion was simply a natural consequence of Earth being in motion rather than stationary at the center. The universe was suddenly much simpler and more elegant than anyone had imagined. But accepting the heliocentric model meant accepting something profoundly unsettling. If Earth was not at the center of the universe, then humanity was not at the center either. We were relegated to being passengers on one planet among several, all orbiting a star that might not be special at all. This was the Copernican principle, and its implications went far beyond astronomy. It suggested that there was nothing unique or privileged about our position in space. We were not the focus of creation. We were not the reason the cosmos existed. We were just another part of it, no more or less important than anything else. The heliocentric model gained support from astronomers like Johannes Kepler, who refined it by showing that planets moved in ellipses rather than perfect circles, and Galileo Galilei, who used the newly invented telescope to observe the moons of Jupiter, orbiting that planet rather than Earth. Here was direct visual evidence that not everything in the heavens revolved around our world. The geocentric model began to crumble, though it would take decades for the heliocentric view to fully replace it in both scientific and popular understanding. But here is where the story takes an unexpected turn. While the Copernican revolution correctly removed Earth from the center of the solar system, it actually kept the idea of a cosmic center intact. In early heliocentric models, the Sun was simply the new center of the universe. The fixed stars were still imagined as a distant sphere surrounding the solar system, with the Sun occupying the privileged central position. Humanity had been demoted from the center, but we still believed there was a center to be found. We had simply moved our understanding of where that center was located. The idea that the universe must have a center, a fixed point from which everything else was organized, remained deeply embedded in how people thought about the cosmos. This makes sense when you think about it. Every system we experience in daily life has a center. A wheel has a hub. A circle has a center point. Even a sphere has a center. Why would the universe be any different? For centuries after Copernicus, astronomers continued to search for the true center of creation, assuming it must exist somewhere, even if we were not occupying that special position. Some thought it might be a distant star. Others imagined vast cosmic structures we had not yet discovered. The search for the center of the universe became one of the great quests of astronomy. The next major breakthrough came in the early 20th century, and it would change everything once again. In 1924, the American astronomer Edwin Hubble, using the powerful Hooker telescope at Mount Wilson Observatory, made a discovery that shattered the existing cosmic paradigm. He proved that the Milky Way galaxy, which contains our Sun and solar system, was not the entirety of the universe as most astronomers had believed. Those fuzzy patches of light that astronomers called nebulae were not clouds of gas within our galaxy. They were entire galaxies in their own right, each containing billions of stars, separated from us by unimaginable distances. The universe was suddenly millions of times larger than anyone had thought, but Hubble was not finished. By 1929, he had made an even more remarkable discovery that would earn him a place among the greatest scientists in history. By studying the light from distant galaxies, Hubble noticed something strange. The wavelengths of light were shifted toward the red end of the spectrum, and the farther away a galaxy was, the more pronounced this redshift became. This redshift indicated that galaxies were moving away from us, and the farther away they were, the faster they were receding. This observation became known as Hubble's law, and it could only mean one thing: the universe was expanding. Think about what this means for a moment. If the universe is expanding now, and we run time backward like rewinding a video, then the universe must have been smaller in the past. Go back far enough, and everything in the cosmos must have been closer together. Keep going, and you reach a point where all the matter and energy in the entire universe was compressed into an infinitesimally small region of space. This realization gave birth to the Big Bang theory, the idea that the universe began approximately 13.8 billion years ago from an incredibly hot and dense state and has been expanding ever since. The Big Bang was not an explosion that happened at a particular location in space, and this is where people often get confused. It was not like a bomb going off that sent matter flying outward from a central point. Instead, the Big Bang happened everywhere simultaneously. Space itself began expanding, carrying matter and energy along with it. Every point in space was once in the same place during the Big Bang, which means every point can legitimately claim to be where the Big Bang happened. There is no special location that can be called the center of the expansion, because the expansion is occurring everywhere at once. To understand this better, astronomers often use the balloon analogy, and it is one of the best ways to visualize what is happening to our universe. Imagine a balloon with dots drawn on its surface. The dots represent galaxies, and the surface of the balloon represents space itself. Now start inflating the balloon. As it expands, what happens to the dots? They all move away from each other. More importantly, no matter which dot you choose to focus on, all the other dots appear to be moving away from it. From any dot's perspective, it looks like it is at the center of the expansion. But here is the crucial insight: there is no actual center on the surface of the balloon. The expansion is happening uniformly across the entire surface. The balloon analogy has a limitation because it tries to represent three-dimensional reality on a two-dimensional surface, but the principle holds. in our actual universe, space itself is expanding in 3 dimensions, and every point in space is moving away from every other point, on average. Galaxies that are gravitationally bound to each other, like those in galaxy clusters, stay together because their mutual gravity is stronger than the expansion of space. But on the larger scales, the universe is stretching, and there is no center to that stretching. The expansion does not have an origin point in space because space itself is what is expanding. This leads to a profound realization. If the universe is homogeneous, meaning it looks roughly the same in every direction and from every location, and if it is isotropic, meaning it has no preferred direction, then it cannot have a center. A center would be a special, unique location, but the cosmological principle, which is supported by all our observations, states that there are no privileged locations in the universe. Every observer, no matter where they are, sees essentially the same universe. They see galaxies receding in all directions according to Hubble's law. They see the same cosmic microwave background radiation coming from all directions. The universe looks the same to everyone because there is no center. This is where our intuition completely fails us. We are used to thinking that anything that expands must be expanding from somewhere, that there must be a point where it all started. But the universe is not expanding into anything, and there was no location where it began. The Big Bang was not an event that happened at a place. It was an event that happened everywhere, and that everywhere has been stretching ever since. The center of the universe, in the traditional sense we might imagine it, simply does not exist. One of the most powerful pieces of evidence supporting our understanding of the universe comes from something called the cosmic microwave background, often abbreviated as CMB. This is radiation that fills the entire universe, coming from every direction in space with almost perfect uniformity. The CMB was discovered accidentally in 1964 by 2 Bell Labs scientists, Arno Penzias and Robert Wilson, who were trying to eliminate mysterious noise from a radio antenna. They eventually realized they were not detecting noise at all, but rather the afterglow of the Big Bang itself. Here is how the CMB came to exist. In the earliest moments after the Big Bang, the universe was unimaginably hot and dense, filled with a plasma of protons, neutrons, electrons, and photons all interacting intensely. The universe was opaque during this time because photons could not travel far before being scattered by free electrons. It was like trying to see through a thick fog, but as the universe expanded, it cooled, and eventually, about 380,000 years after the Big Bang, it reached a temperature low enough for electrons to combine with protons to form the first neutral hydrogen atoms. This event is called recombination, and it changed everything. Once recombination occurred, photons were suddenly free to travel through space without constantly being scattered. The universe became transparent. Those photons have been traveling through space ever since, and as space has expanded, their wavelengths have been stretched from visible light all the way into the microwave part of the electromagnetic spectrum. Today, we detect this radiation as a faint microwave glow with a temperature of about 2.7 Kelvin, just a few degrees above absolute zero. The CMB is everywhere, and it looks almost exactly the same in every direction we observe. The incredible uniformity of the CMB is powerful evidence for the cosmological principle. If the universe had a center, we would expect the CMB to look different in different directions. We might see hotter regions in one direction and cooler regions in another, indicating some kind of structure or gradient related to a central point. But that is not what we observe. The CMB is uniform to better than 1 part in 100,000 across the entire sky. This tells us that the early universe was remarkably homogeneous, with matter and energy distributed almost perfectly evenly in all directions. There are tiny fluctuations in the CMB temperature, variations of only a few millionths of a degree, and these are incredibly important because they represent the seeds of all structure in the universe. Regions that were slightly denser than average eventually collapsed under their own gravity to form galaxies, stars, and planets. But these fluctuations are random and distributed uniformly across space. They do not point to any kind of center or preferred location. The CMB confirms that the universe has no special point, no cosmic downtown from which everything else is organized. It looks the same from every vantage point, at least on the largest scales. When astronomers map the CMB in detail using satellites like the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft, they are essentially looking at a snapshot of the universe when it was only 380,000 years old. This is the oldest light we can see, a baby picture of the cosmos, and that baby picture shows us a universe without a center, a universe that already looked the same in all directions even when it was less than 1% of its current age. The fundamental structure of reality has been centerless from nearly the beginning. Now we need to address an important distinction that often causes confusion. While the universe as a whole does not have a center, you do occupy the center of something called the observable universe, and so does every other observer. The observable universe is the region of space from which light has had time to reach us since the Big Bang. Because the universe is about 13.8 billion years old and light travels at a finite speed, there is a limit to how far we can see. Beyond that limit, light has not had enough time to reach us yet, so we cannot observe what lies there. The radius of the observable universe is not simply 13.8 billion light-years though, because space has been expanding during the time that light has been travelling toward us. When we account for this expansion, the current distance to the edge of the observable universe is approximately 46.5 billion light-years in every direction. This creates a sphere, centered on Earth, with a radius of 46.5 billion light-years. Everything within that sphere is potentially visible to us, given powerful enough telescopes. Everything beyond it is not, at least not yet. But here is the crucial point. This sphere is centered on us only because we are the observers. An alien astronomer on a planet in a distant galaxy would have their own observable universe, a sphere of the same size centered on their location. Their observable universe would overlap with ours in some regions, but extend into space we cannot see in other directions. Every observer in the universe is at the center of their own observable universe, but none of them are at the center of the universe itself. The observable universe is a subjective concept based on the observer's position and the finite speed of light, while the actual universe is objective and centerless. This creates some fascinating implications. Because different observers have different observable universes, there is almost certainly much more to reality than any single observer can see. Our observable universe contains an estimated 2 trillion galaxies, but the entire universe could be vastly larger, perhaps even infinite in extent. If the universe is infinite, then it has always been infinite, even at the moment of the Big Bang. The Big Bang didn't happen at a point that then expanded into surrounding space. It happened throughout an already infinite space, with density and temperature dropping as space stretched. The edge of the observable universe is not a physical boundary. It is simply the limit of our vision, determined by how far light has travelled since the Big Bang. As time passes and the universe continues to age, we might expect the observable universe to grow as light from more distant regions reaches us. However, there is a complication, and it has to do with something called dark energy. In 1998, two independent teams of astronomers studying distant supernovae made a shocking discovery that would earn them the Nobel Prize in Physics. They were observing Type Ia supernovae, which are stellar explosions that reach predictable brightnesses and can be used as standard candles to measure cosmic distances. The teams expected to find that the expansion of the universe was slowing down over time due to the gravitational attraction between galaxies. Instead, they found the opposite. The most distant supernovae were dimmer than expected, indicating they were farther away than they should be if expansion were decelerating. The expansion of the universe was not slowing down, it was speeding up. This discovery required something completely unexpected to explain it, a form of energy that permeates all of space and acts as a kind of anti-gravity, pushing the universe to expand faster and faster. Scientists called this mysterious force dark energy, and it is now thought to make up about 68% of the total energy content of the universe. We do not know what dark energy actually is. It might be a property of space itself, a cosmological constant as Einstein once proposed, or it could be something more exotic that changes over time. But whatever it is, it has profound implications for the fate of the universe and for the question of cosmic centers. Because of dark energy, the expansion of the universe entered an accelerating phase roughly 5 billion years ago. Galaxies that are not gravitationally bound to each other are moving apart at an ever-increasing rate. This means that distant galaxies are receding from us faster and faster, and eventually, many of them will be moving away faster than the speed of light relative to us. This does not violate Einstein's special relativity because it is space itself that is expanding, not the galaxies moving through space. But it does create a cosmic horizon beyond which we will never be able to see, no matter how long we wait. In fact, because of accelerating expansion, the observable universe will not continue to grow indefinitely. There is a future visibility limit, a boundary beyond which light from distant objects will never reach us because those objects are receding too quickly. Galaxies that are currently beyond this limit will remain forever invisible, and galaxies that are currently visible will eventually cross this boundary and fade from view as they accelerate away from us. In the far future, observers in our galaxy will look out and see a much emptier universe, with only the galaxies in our local gravitationally bound group remaining visible. The rest will have been carried away by dark energy. Recent studies in 2025 have even begun to question whether the expansion is truly accelerating or might be slowing down, which would overturn decades of established understanding about dark energy. If confirmed, such findings would require a complete rethinking of cosmic expansion, but they would not change the fundamental fact that the universe lacks a center. Whether expansion is accelerating, decelerating, or remaining constant, the expansion itself is uniform in all directions from every point. Dark energy, whatever it might be, does not emanate from a central location. It is a property of space itself, present everywhere equally. The existence of dark energy and the accelerating expansion it causes reinforce the idea that the universe has no center. If there were a central point from which expansion originated, we would expect to see some directional preference in how fast galaxies are receding. Galaxies on one side of the sky might be moving away faster than galaxies on the opposite side. But observations show that expansion is isotropic. It occurs at the same rate in all directions, which is exactly what we would expect from a centerless expansion. Everything we have discussed so far rests on a fundamental assumption called the cosmological principle. This principle states that the universe is both homogeneous and isotropic on the larger scales. Homogeneous means the universe looks roughly the same at every location. Isotropic means it looks the same in every direction. Together, these properties imply that there is no privileged position in the universe, no special location that is fundamentally different from any other. And if there is no privileged location, there can be no center. The cosmological principle is an extension of the Copernican principle, which removed Earth from a central position in the solar system. The cosmological principle takes this further, suggesting that not only is Earth not at the center of the universe, but there is no center at all. Every observer, regardless of where they are located, should see essentially the same universe. Galaxies recede according to Hubble's law. The cosmic microwave background has the same temperature in all directions, and the large-scale structure of galaxy clusters and superclusters is statistically similar everywhere. This principle is supported by extensive observational evidence. When astronomers map the distribution of galaxies across vast regions of space, they find that while there are structures like galaxy clusters, walls, and voids, these structures are distributed randomly with no overall pattern that points to a center. The universe looks like a cosmic foam, with galaxies concentrated in filaments and sheets surrounding large empty regions, but this foam extends in all directions with no apparent origin point. On scales larger than about 300 million light-years, the universe becomes remarkably uniform. The cosmic microwave background provides even stronger support for the cosmological principle. Its extreme uniformity across the entire sky tells us that the early universe was homogeneous and isotropic to an extraordinary degree. The tiny fluctuations we observe in the CMB are consistent with random quantum variations that occurred during cosmic inflation, a brief period of exponentially rapid expansion in the first fraction of a second after the Big Bang. These fluctuations became the seeds of all structure in the universe, but they show no directional preference or indication of a central point. However, the cosmological principle is an assumption, and like any scientific assumption, it must be continually tested against observations. Some cosmological models have challenged the principle, suggesting that we might occupy a special location after all. For example, some alternative theories propose that Earth is near the center of a finite spherical universe, which could explain certain anomalies in observational data. Other models suggest that the universe might have large-scale inhomogeneities that violate the cosmological principle. These are minority views, and most evidence continues to support the standard model, but they remind us that science must always remain open to new evidence. If the cosmological principle is correct, and all evidence suggests it is, then the universe cannot have a center in any meaningful sense. A homogeneous, isotropic universe is fundamentally different from the centered spheres imagined by ancient astronomers. It is a universe where every location is equivalent, where no observer is more central than any other. This is a universe that does not care about us, that has no special place reserved for humanity or Earth. It is a universe of stunning democracy where every point in space has equal standing. To fully understand why the universe has no center, we need to delve into Albert Einstein's general theory of relativity, published in 1915. This theory revolutionized our understanding of gravity and space itself. Einstein showed that gravity is not a force in the traditional sense, but rather a consequence of the curvature of space-time. Massive objects like stars and planets warp the fabric of space-time around them, and other objects move along the curved paths created by this warping. This is gravity. General relativity also provides the mathematical framework for understanding the universe as a whole through what are called the Friedmann equations, named after the Russian physicist Alexander Friedmann. These equations describe how the scale of the universe changes over time based on its energy content and geometry. Depending on the total density of matter and energy, the universe can have one of three possible shapes: closed and finite, like the surface of a sphere; open and infinite, like a saddle extending forever; or flat and infinite, like an endless plane. Current observations, particularly from the cosmic microwave background, indicate that our universe is very close to being flat. A flat universe is infinite in extent and has no center. You could travel in any direction forever without reaching an edge or returning to your starting point. In contrast, a closed universe would be finite, but also have no center in the same way that the surface of a sphere has no center point on the surface itself. The center of a sphere exists in a higher dimension, not on the two-dimensional surface. Similarly, if our universe is closed, its center would exist in a higher spatial dimension that we cannot access or perceive. The mathematics of general relativity, encoded in the Friedmann equations, naturally leads to solutions where the universe is homogeneous and isotropic, exactly as the cosmological principle suggests. These solutions describe a universe that expands uniformly in all directions with no preferred location. When cosmologists model the Big Bang and the subsequent evolution of the cosmos, they use these equations, and nowhere in them is there a center. The expansion they describe is intrinsic to space itself, not an explosion from a point. Einstein himself initially struggled with some implications of his own theory. His original equations predicted that the universe should either be expanding or contracting, but at the time, most scientists believed the universe was static and unchanging. To make his equations compatible with a static universe, Einstein added a term called the cosmological constant, a form of energy that would perfectly balance gravitational attraction and prevent collapse. When Hubble later discovered that the universe was indeed expanding, Einstein reportedly called the cosmological constant his biggest blunder. Ironically, we now know that something very much like a cosmological constant, what we call dark energy, actually does exist and is driving the accelerating expansion of the universe. The space-time described by general relativity is dynamic and responsive to the matter and energy within it. On local scales, mass creates curvature that we experience as gravity. On cosmic scales, the overall distribution of matter and energy determines whether the universe is open, closed, or flat, and how quickly it expands. But in all cases, for a homogeneous and isotropic distribution of matter, there is no center. The geometry of space-time simply does not support the existence of a central point. The Big Bang theory explains a great deal about how the universe evolved from a hot, dense state to its current form, but it leaves some important questions unanswered. Why is the universe so uniform on large scales when different regions should not have had time to exchange information and equalize their temperatures? Why is the universe so close to being geometrically flat when small deviations from flatness should have been amplified over time? These puzzles led to the development of inflation theory in the early 1980s. Cosmic inflation proposes that in the first tiny fraction of a second after the Big Bang, roughly from 10 to the minus 36 seconds to 10 to the minus 32 seconds, the universe underwent a period of exponentially rapid expansion. During this brief instant, the universe grew by an enormous factor, perhaps by 10 to the 26th power or more. Space expanded faster than the speed of light, which is allowed because it is space itself that is expanding, not objects moving through space. This incredible growth spurt solved the horizon problem by explaining how different regions of the universe could look so similar, despite being too far apart to have ever been in contact. Before inflation, these regions were close enough together to reach thermal equilibrium. Inflation then stretched them to opposite sides of the visible universe. Inflation also explains why the universe is so flat. Any initial curvature would have been stretched out by the exponential expansion, like inflating a balloon to an enormous size makes its surface appear flat to an ant walking on it. After inflation ended, the universe continued to expand, but at a much slower rate, following the standard Big Bang evolution we observe today. The tiny quantum fluctuations that existed during inflation were also stretched to cosmic scales, creating the density variations that eventually became galaxies and all the structure we see. These predictions of inflation have been confirmed by detailed observations of the cosmic microwave background. What caused inflation to begin and end remains one of the great mysteries of cosmology. Various models propose different mechanisms involving exotic energy fields that existed in the early universe. One intriguing possibility, suggested by physicist Andre Linde, is that inflation might be eternal. In this scenario, inflation is constantly occurring somewhere in a vast multiverse, with different regions occasionally dropping out of the inflationary state to form bubble universes like our own. Our entire observable universe would be just one such bubble in an eternally inflating cosmic foam. If eternal inflation is correct, then our universe might be part of something vastly larger, a multiverse of infinite extent containing countless bubble universes, each potentially with different physical laws. But even in this picture, there is no center. The inflationary process occurs throughout an infinite space with no preferred location. Each bubble universe would be centerless, just as our own appears to be. The concept of a cosmic center becomes even more meaningless in a multiverse scenario because there is no single universe to have a center. Inflation remains a theory, though it is strongly supported by observations. It provides elegant solutions to problems that the standard Big Bang model struggled with, and its predictions match what we observe in remarkable detail. Whether or not inflation happened exactly as current models describe, the fact remains that our universe shows no evidence of having expanded from a central point. The uniformity we observe on large scales could only result from a process that affected all of space equally, with no special locations or directions. The concept of a multiverse takes the question of cosmic centers in a radical new direction. If our universe is not the only universe, if there are countless others existing in parallel or in distant regions of a larger reality, then perhaps the question of where the center of the universe is becomes meaningless in a different way. Perhaps we should be asking about the center of the multiverse instead, though that question may be equally unanswerable. There are several different multiverse theories, and they propose wildly different pictures of reality. One version, sometimes called the Level 1 multiverse, simply extends the idea of an infinite universe. If space is truly infinite, then by the laws of probability, every possible arrangement of matter must occur somewhere. That means there must be infinite copies of Earth, of you, of every possible variation of history. These parallel regions exist in our own universe, just unimaginably far, away beyond our observable horizon. This multiverse has no center because it is still fundamentally our own infinite universe. The Level 2 multiverse includes separate regions of space with different physical constants or laws. This could arise from eternal inflation, where different bubble universes emerge from the inflationary field with different properties. Perhaps in some bubble universes, electromagnetism is stronger than in ours. Perhaps in others, there are more or fewer dimensions of space. These universes might be separated by vast distances or by insurmountable energy barriers. They could have different centers or no centers, depending on their individual geometries, but the multiverse as a whole would have no center if the inflationary field is infinite and produces bubbles continuously. The Level 3 multiverse comes from the many worlds interpretation of quantum mechanics. In this view, every time a quantum measurement occurs, reality splits into multiple branches, one for each possible outcome. Every quantum event creates new universes, leading to an ever-branching tree of parallel realities. In one universe, you made one choice. In another, you made a different choice. Both universes are equally real, just separated in some abstract space of possibilities. This multiverse is not spatial at all, so the question of a center does not even make sense in geometric terms. Finally, the Level 4 multiverse is the most radical proposal. It suggests that every mathematically consistent set of physical laws describes a universe that actually exists somewhere in the ultimate multiverse. Our universe, with its specific constants and forces, is just one possibility among an infinite number of others, each following different mathematical rules. Some might have time running backward, others might have 11 dimensions, still others might have physics completely unrecognizable to us. If this is true, then the multiverse is not a physical space at all, but rather a space of mathematical possibilities, and the concept of a center is completely meaningless. All multiverse theories remain speculative. We have no direct evidence that other universes exist, and it may be fundamentally impossible to obtain such evidence if those universes are causally disconnected from our own. Some scientists argue that multiverse theories are not even scientific because they make no testable predictions. Others counter that multiverses are natural consequences of well-established theories like inflation and quantum mechanics, and that we should take them seriously. Whatever the truth, multiverse theories emphasize just how far we have come from the simple geocentric models of ancient times. The question has expanded from where is the center of the universe to whether there is even a single universe to have a center. While the universe as a whole has no center, we should note that there are plenty of local centers within it. Every gravitationally bound system has a center of mass, a point around which its components orbit. Earth orbits the center of mass of the Earth-Sun system, which is actually inside the Sun because the Sun is so much more massive. The Sun orbits the center of mass of the Milky Way galaxy, located about 26,000 light-years away in the direction of the constellation Sagittarius. This galactic center is marked by a supermassive black hole called Sagittarius A star, with a mass of about 4 million suns. The Milky Way, in turn, is part of the local group of galaxies, which includes the Andromeda Galaxy, the Triangulum Galaxy, and dozens of smaller dwarf galaxies. The local group has a center of mass located somewhere between the Milky Way and Andromeda, though precisely where depends on the mass distribution of dark matter, which we cannot directly observe. The local group is part of the Virgo supercluster, an even larger structure containing thousands of galaxies, and that supercluster is part of an even larger structure called Laniakea, which spans 500 million light-years and contains roughly 100,000 galaxies. All of these structures have centers, but here is the key point. These are local centers created by gravity pulling matter together into hierarchical structures. They are not centers of the universe. They are just concentrations of mass in particular regions of space. Gravity can create a center wherever matter clumps together, but because gravity pulls equally on all objects across the universe, and because matter is distributed roughly uniformly on the largest scales, these local centers are scattered throughout space with no overall pattern. The universe is filled with centers, which is another way of saying it has no center. Imagine scattering marbles on a table and then looking at each marble as the center of circles drawn around it. You could do this for every marble, creating overlapping circles of different sizes. Every marble would be at the center of its own system, but the collection of marbles as a whole would have no inherent center unless you arbitrarily chose one. The universe is similar, but in 3 dimensions and on a cosmic scale. Every galaxy, every star, every planet is at the center of its own gravitational influence. But the cosmos as a whole has no special point that can claim to be the center of everything. This proliferation of local centers in a centerless universe is actually a beautiful feature of cosmic structure. It means that complexity and organization can arise anywhere. Galaxies can form, stars can ignite, planets can coalesce, and life can emerge in any region of space. There is no privileged location where these things happen. The conditions for structure and complexity are universal, dependent on local physics rather than proximity to some cosmic downtown. In a very real sense, everywhere is the center when it comes to the potential for interesting phenomena to occur. The realization that the universe has no center carries profound philosophical implications that extend far beyond astronomy and physics. For most of human history, we believed we occupied a central position in creation, and this belief shaped our entire worldview. We saw ourselves as the reason for existence, the focus of divine attention, the purpose for which the cosmos was made. The discovery that we do not occupy a central position has been called the greatest demotion in history, but it is also a liberation. When we believed Earth was the center of the universe, it imposed certain expectations and responsibilities. We had to be special. We had to matter in a cosmic sense. Our actions had to have significance that echoed through the spheres of the heavens. The removal of Earth from the center initially created an existential crisis for many people. If we are not central to creation, then what are we? What is our purpose? Do we matter at all in the vast indifference of space? These questions troubled thinkers for centuries after Copernicus, and they continue to resonate today. But there is another way to look at it. If there is no center to the universe, then no location is more important than any other. This means Earth is not less important for not being central. Every place is equally valid, equally real, equally part of the cosmos. We are not special because we are central. We are special because we exist at all, because we are part of the universe that has organized itself to contemplate its own existence. The fact that this could happen anywhere rather than at some unique location does not diminish it. If anything, it makes it more remarkable. The centerless universe also has implications for how we think about meaning and purpose. In a universe with a center, one might imagine that meaning flows from that center, that there is some cosmic authority or fundamental truth located at the heart of reality. In a centerless universe, meaning cannot come from outside or from some privileged location. It must be created locally, emerging from the interactions of matter and energy, from the complexity of life, from the consciousness that arises in biological systems. We are not given meaning by our position in space. We create meaning through our existence and our choices. This perspective aligns with modern secular and scientific worldviews that see humans as products of natural processes rather than special creations. But it need not be incompatible with religious or spiritual perspectives either. Many theologians and philosophers have argued that a God or ultimate reality that is truly universal would not need a center, would not be localized in space at all. The sacred, if it exists, must be everywhere or nowhere, not tied to a particular cosmic address. The shift from geocentrism to a centerless cosmos need not diminish the possibility of transcendence. It merely relocates it from a place to a state of being. The cosmological principle, which tells us the universe is the same everywhere, also suggests a deep democracy written into the fabric of reality. No observer is privileged. No location is favored. The laws of physics operate the same way in every galaxy, on every planet, in every region of space and time. This uniformity is what makes science possible. We can study the universe from our tiny corner of it and reasonably expect our discoveries to apply everywhere, because there is no cosmic hierarchy that would make different regions fundamentally different. The universe may not care about us, but it also does not care about anything else more than us, and there is a strange comfort in that equality. So after this long journey through history, observation and theory, we arrive at the answer to our original question. Where is the center of the universe? The answer is that there is no center. The universe does not have a central point from which it expands or around which it is organized. Every location in space is equally valid, equally central or peripheral, depending on your perspective. You are at the center of your observable universe, but so is every other observer everywhere. The universe is centerless because it is homogeneous and isotropic, because space itself is what is expanding, and because the Big Bang happened everywhere simultaneously rather than at a particular location. This answer is counterintuitive and difficult to visualize because it goes against every experience we have with expanding things in daily life. When a balloon inflates, it expands from its center outward into the room around it. When a bomb explodes, debris flies away from the point of detonation. But the universe is not like these examples. It is not expanding into anything. There is no outside. There was no point where it began. The expansion is intrinsic to space itself, uniform in all directions, with no origin and no destination. The lack of a cosmic center is not a failure of our observations or a limitation of our theories. It is a fundamental feature of reality as best we understand it. The cosmological principle, supported by countless observations from galaxy surveys to the cosmic microwave background, tells us that the universe is the same everywhere on large scales. A homogeneous, isotropic universe cannot have a center. General relativity, our best theory of gravity and space-time, describes a cosmos that expands uniformly without a central point. Inflation explains how the universe came to have the properties we observe without requiring a special location. Of course, our understanding of the universe is incomplete and may change as we gather more data and develop better theories. There are still mysteries we cannot explain, like the nature of dark matter and dark energy, the exact mechanism of inflation, what if anything came before the Big Bang, and whether we live in a multiverse. Future discoveries could conceivably challenge the cosmological principle or reveal structures that violate homogeneity on the largest scales. Science must always remain open to revising its conclusions based on new evidence. But based on everything we currently know, from observations spanning decades and theoretical frameworks built on Einstein's century-old insights, the evidence overwhelmingly points to a universe without a center. This is one of the great discoveries of modern science, as revolutionary in its way as the revelation that Earth orbits the Sun. We have learned that we do not occupy a special place in space, but we have also learned something more subtle and perhaps more profound. There is no special place. The universe is indifferent to location, granting no cosmic real estate more importance than any other. In a centerless universe, every point is equivalent, and every observer, wherever they may be, sees a cosmos that appears to be organized around them. Understanding that the universe has no center changes how we think about our place in existence, but it also raises new questions that drive current research in cosmology and physics. If the universe is centerless and potentially infinite, does that mean there are infinite versions of us somewhere beyond the observable horizon? If eternal inflation is correct and new bubble universes are constantly forming, could we someday detect evidence of these other universes, perhaps as subtle patterns in the cosmic microwave background where bubbles collided with our own? If the multiverse is real, does each universe have its own geometry and structure, or are there overarching principles that apply to all of reality? These questions push the boundaries of what we can know and what counts as science. Some researchers argue that we should embrace testable predictions of theories like inflation and quantum mechanics, even if those predictions include unobservable entities like other universes. Others insist that science must restrict itself to what can be empirically verified, which means multiverse speculation may be interesting philosophy but not physics. The debate continues, and it represents the frontier of human knowledge about the cosmos. What is not in doubt is that our understanding of the universe has transformed dramatically over the past century. We have gone from viewing the cosmos as a small collection of stars and nebulae, all contained within the Milky Way, to recognizing a universe of trillions of galaxies extending billions of light years in every direction. We have discovered that space itself is expanding, carrying those galaxies away from each other at speeds that increase with distance. We have detected the faint afterglow of the Big Bang still filling all of space. We have measured the age of the universe to within a few million years out of 13.8 billion. We have mapped the distribution of matter on the largest scales and found it consistent with a centerless, homogeneous cosmos. These achievements represent some of humanity's greatest intellectual accomplishments, the product of centuries of observation, experimentation, mathematical development, and theoretical insight. The fact that we can know anything at all about the overall structure and history of the universe is remarkable. The fact that we can be confident the universe has no center, despite how strange that conclusion seems, is a testament to the power of the scientific method to reveal truths that go against intuition and common sense. Yet for all we have learned, the universe remains deeply mysterious. We do not know what constitutes 95% of its energy content, having given those unknown components the placeholder names dark matter and dark energy. We do not know if space is finite or infinite, or whether the geometry of the universe is exactly flat or just very close to it. We do not know what caused the Big Bang, or if that question even makes sense. We do not know if our universe is the only one or one among many. We have answered the question of where the center of the universe is, but in doing so, we have opened up vast new territories of ignorance that future generations of scientists will explore. The search for the center of the universe has been one of humanity's longest and most profound quests. For thousands of years, we believed we had found the answer, first placing Earth at the center, then the Sun, then searching for some other cosmic focal point among the stars. Each time we thought we had located the center, further discoveries revealed we were wrong. We were projecting our terrestrial intuitions onto a cosmos that operates by different rules. The center we kept searching for was a fiction, a holdover from a time when we thought the universe was small, static, and built for us. The true answer, revealed gradually through centuries of observation and thought, is more radical than anyone imagined. The universe has no center because every point within it is equivalent. You are at the center of your observable universe, and so is every alien astronomer on every planet around every star in every galaxy across the cosmos. We are all central, and none of us are. The universe is a democracy of space where no location holds special status, where the laws of physics apply uniformly, and where the potential for complexity, structure, and even life exists everywhere. This centerless cosmos is the universe we actually inhabit, as opposed to the centered universes of our imagination and ancient cosmologies. It is a universe that cares nothing for us, that was not made with us in mind, that would continue expanding and evolving regardless of whether Earth existed or life had ever emerged. But it is also a universe that is comprehensible to our minds, whose secrets we can uncover through observation and reason, whose structure follows mathematical laws we can discover and understand. In a centerless universe, we have found our place not through special location, but through our ability to look outward and see the cosmos as it truly is. The journey from geocentrism to the cosmological principle represents one of the great intellectual revolutions in human history, comparable to the development of evolutionary theory or quantum mechanics in terms of its impact on how we understand ourselves and our place in nature. We have learned humility, that we are not the focus of creation, but we have also learned capability, that we can understand reality even when it defies our intuitions. We have learned that the universe is larger, stranger, and more wonderful than our ancestors ever imagined, and that knowing the truth about it, even when that truth removes us from a central position, is more valuable than comfortable illusions. So the next time you look up at the night sky and see stars scattered across the darkness, remember that you are seeing a universe without a center, a cosmos that expands uniformly in all directions with no origin point and no preferred location. Remember that those distant galaxies are racing away from us and from each other as space itself grows larger. Remember that the faint microwave hiss of the cosmic background radiation is reaching you from every direction, a signal from the beginning of time that looks the same to every observer everywhere. And remember that your question about where you are in all of this vastness has a profound answer. You are nowhere special, and you are right at the center, and somehow both of those things are true at once in a universe more subtle and more magnificent than any cosmos we could have invented ourselves.